Hi, my name is Valerie Burge, and this is my topic presentation on the encapsulation of ferulic acid in nanoparticles. First, I'd like to talk about nanotechnology in cosmetics, specifically two moving parts, the nanotechnology, which is technology used to manipulate particles within a range of 1 to 100 nanometers, and then cosmeceuticals, which is any product that incorporates a biologically active ingredient that benefits the surface to which it's applied. So we have a product that is good for our skin, we apply it to the skin and is absorbed, and it makes our skin better. Now, this can be done through a variety of different methods, but we'll go over one of them later. The benefits of using nanocosmetics is that we are able to control the release of an active ingredient through a variety of different methods, allowing for a slow release of an active ingredient, meaning our skin is benefited for a longer period of time by the product. Additionally, this adds some long-term stability. Because of this high entrapment efficiency, we get more of the product, and it also allows for more shelf stability than conventional cosmetic products. The main ingredient we're going to be looking at in this presentation is ferulic acid. This is an antioxidant that is found in plants and is most commonly used in skincare and cosmetic products. This is because of its known effects of reducing inflammation, its anti-aging effects, and the little bit of UV protection that it provides. The problem with using ferulic acid, though, is that it has poor long-term stability and low aqueous solubility. So when it is in a cosmetic product, whether it be in storage or whatever matrice it's in, if it's at a basic pH level or if it's within high or changing temperatures, if it's exposed to light or in the presence of incompatible ingredients, the ferulic acid can degrade or engage in side reactions, and ultimately your product will no longer have the added benefits it originally intended to. So, previous research involving the use of ferulic acid in cosmetic products has attempted to encapsulate it. And this can be done by encapsulating the ferulic acid in an oil or lipophilic payload. However, these previous research attempts have been unsuccessful due to the fact that the microcapsules were unable to deliver the active agent to the skin due to how large they were. Now, in the 2020 research by the Gupta group, they looked at the encapsulation of ferulic acid in lipid nanoparticles as an antioxidant to the skin. And they did this through two main pieces: the experimental studies, in which they tried to formulate a ferulic acid-loaded lipid nanoemulsion in an aqueous environment, and then through molecular dynamic simulations, in which they were able to visualize these nanoemulsions and provide insight into the structural, energetic, and dynamic properties of the nanoemulsion and ultimately the nanoparticles. Now, in order for the successful formulation of these lipid-based nanoparticles, solubility is a major prerequisite. So ferulic acid has to be able to, at a high enough temperature, become miscible with a lipid in order to create these nanoparticles. This was able to be done by determining that ferulic acid was the most compatible with the lipid glucose 5013, which actually isn't just one molecule. It is a combination of PEG-32 stearate and glycerol distearate, which are visualized to the right. The general methodology that the Gupta group used is threefold. Firstly, the emulsification was performed by melting glucose 5013 at 70 degrees Celsius, which is that high temperature, and then dissolving the ferulic acid in it. Then, using hot water, this mixture was homogeneously dispersed, and that was ultrasonicated in order to create the nanoemulsion. And in order to actually determine what concentration of ferulic acid created the best nanoemulsion, the presence of unencapsulated ferulic acid was identified under a cross-polarized light microscope. Now, one of the unique parts of this research is cryothem imaging, which is cryogenic transmission electron microscopy, which is able to produce images that allows for, in this specific research, 29,000 times magnification, which what can be found using this is not only accurate measurements for the size of these nanoparticles, but it also allows the researchers to look at the shape and morphological features of these nanoparticles. And one of these cryo-TEM images is actually shown to the left. Another unique feature of this research is the molecular dynamics simulation models. Now, these were able to create generalized visualizations of the mixtures made by the nanoemulsion. This was done using optimized versions of the molecules in order to look at certain previously unexplained phenomena, such as the location of the ferulic acid within the nanoparticle, the orientation of the lipids within the nanoparticle, the causes of instability when higher concentrations of ferulic acid is used, along with looking at the changes in structural and energetic properties during nanoemulsion and also of the nanoparticle in general. Gupta research group found that the best concentration for ferulic acid in order to get successful formation of the nanoparticle was 0.5% weight in solution. Additionally, they found that the nanoemulsion process was done by a very quick assembly of the lipid molecules into many small nuclei. Now, you can see this in the molecular dynamic simulations in which we have all of these little green ferulic acid molecules and then these large lipid structures that over time create these small little nuclei that ultimately create our final larger spherical cluster of the nanoparticle. Now, what they found is that during the solidification process, the shape and size of the nanoparticle remained generally unchanged, but the mobility of the nanoparticle was significantly reduced. Now, this is important because it was found that the ferulic acid in these simulations was towards the surface of the nanoparticle, as seen here. And all of the hydrophobic parts of the lipid molecules resided inside at the core of the particle. In order to better contextualize these results, there's a couple different resources that I intend on using in my final seminar presentation, and that includes the role of nanotechnology for design and development of cosmeceutical products. And this specifically discusses the benefits of nanoemulsion for cosmetic usage. So in that little beginning section where I was talking about nanotechnology and cosmeceuticals, I could lay out a better foundation describing why it's important to use nanoemulsion and how this largely applies to the use of ferulic acid in this research. Additionally, I want to look at the characterization of physiochemical properties of ferulic acid. This is actually a paper that was cited by the Gupta group in their research, and it goes into much more depth on the specific issues ferulic acid has with long-term stability, and it also discusses a little bit about the solubility of ferulic acid and lipids. Additionally, I want to look at lipid-based nanocarriers, a promising drug delivery system for topical application, which will allow me to get a better, more in-depth analysis of the mechanism by which encapsulation of the ferulic acid takes place, and also how the drug delivery system works. So how the ferulic acid within the nanoparticle is deposited in the skin, and how that broadly relates to cosmeceuticals as a whole. My goal throughout all of this research is to use the primary paper by the Gupta group and this supplementary material in order to create our 30-minute seminar presentation on the use of lipid-based nanoemulsion to improve the long-term stability of ferulic acid and ultimately prove its use for cosmeceutical purposes. I plan on doing this by focusing on a specific group of methods in my presentation. As previously stated, nanotechnology and cosmeceuticals is the basis of this, but I more in depth want to look at the long-term stability and solubility of ferulic acid as well, along with the process of encapsulation and nanoemulsion in order to better demonstrate how these processes work and how they apply to ultimately creating the nanoparticle. Additionally, I want to talk about the importance of the orientation of the lipids within these nanoparticles and why they orientate themselves this way, and how that plays into the simulations that we got and what those simulations are actually telling us. Additionally, I want to talk about the usage of light spectroscopy in order to visualize unencapsulated ferulic acid, so better explaining how those results were found and relating it back to chemistry that we are more familiar with. And then just getting a better understanding of the results from all of this information, and then applying that to the broader application of cosmeceuticals as a whole, as well as using topical treatments in pharmaceuticals. Here are the sources that I used for this presentation, and thank you for watching.